In today's tutorial we will have a look at a very special substitution reaction. Here we have a cyclopropane derivative with a bromine and a chloride atom sitting at the cyclopropane, and as the reaction partner we have this thiophenolate. If it reacts with each other in a substitution reaction, then we will produce sodium bromide and this thioether. So, how could the mechanism work? Well, overall, it is a substitution reaction, and with substitution reactions, nucleophilic substitution comes to our mind at first. So, what kind of nucleophilic substitution reactions do we know? SN1 and SN2 process. With the SN1 process, we have a carbocation as a reactive intermediate. With the SN2 process, we have such a transition state where the nucleophile is approaching while simultaneously the bromide is leaving the molecule. But both mechanisms, SN1 and SN2, have the same problem in this special case, because both this reactive intermediate and this transition state need an sp2 hybridization, either for the reactive intermediate or for the transition state. That central carbon is sp2 hybridized. So, but sp2 hybridization means the typical bond angle is 120 degrees, and this 120 degrees is far more away from the 60 degrees typical within the cyclopropane ring, and also, well, if we compare it with the sp3 hybridization, the 109 degrees are more close to the 60 degrees we are in need of. Well, please remember, the center of the highest electron density between those carbon-carbon bonds here is not under the direct line, at the direct line, but a little bit outside, here and there. We are calling that, therefore, banana bonds. So, this change in hybridization from sp3 to sp2 would implement even more ring strain, and that means this has a very high energy barrier. It just doesn't work, and therefore under normal thermal reaction conditions this reaction doesn't work at all. But there is an interesting mechanism which could work, and it works indeed. It's the SET process. SET means single electron transfer. If we add some light and irradiation with light, this is the abbreviation. This is the abbreviation for a photochemical reaction. Then electrons are lifted up to a higher energy level, and if we lift up the electron of this thiophenolate, then with, while approaching such a reaction partner, this electron can be transferred from here to there. What would be the result? So we have at the thiophenolate one electron less. That means we would get to a radical cation. On the other hand, here at this cyclopropane, derivative, we have one electron more. That means we have a radical anion. So where is this electron sitting? Well, it will go into an antibonding molecular orbital, preferentially of that carbon-bromide bond. Well, if we have that radical anion, this can easily lose its bromide, giving rise to this radical where we have the electron remaining, the radical electron remaining in an sp3 hybrid orbital. So, no need in change of the hybridization at that carbon. On the other hand, this radical cation will lose the sodium cation, sodium bromide is formed, and what will remain? This thiophenol radical. Since this reaction takes place when those two reaction partners get together and we have the irradiation by light at the right time, then those radical anion and this radical cation will sit within a solvent cage, and therefore the recombination will take place between those two radicals. And recombination forming a bond with this radical electron and that radical electron leads to our product. Thanks for listening.